Right, hey New Scientist Twitter. So, third time I've tried this video, keep running out of memory and things. Let's see what happens. Anyway, I want to take you through an exercise um, that I did, and I think many people do, when they're into evolutionary biology and they're beginning to learn to code and they want to look at the technical details of evolutionary biology and understand them a bit better. So, and that exercise is to take one of the popular exists and to write some computer code that will perform a simulation based upon those models. So in this case, the model is called the fisher-wright model, which is just a model of how the biological population works that can be expressed in such simple mathematical terms that one can extrapolate from it easily and make very real and indeed experimentally backed up in often cases predictions about real life systems. Let's jump right in with it. What I thought I would do is simulate evolution in a population moving through time, and we'd look at, in particular at one locus. Let's presume we're just interested in the one locus. So a locus can have multiple different alleles at any given time. The alleles have to come into being through mutation. So, for example, if the locus describes a gene, which is likely, if it's something of interest, then a mutation could change the splicing, or it could be a point mutation that changes the amino acid sequence of the gene, or potentially it just could delete the gene. I mean, that's a legitimate allele at the locus. As long as it keeps segregating in the population as the same sort of unit, then it's a different version of the locus is an allele. So in order to do that, I think what we need to do first is. Oh, by the way, I'm just going to describe this, assuming that people watching know something about R and probably have some experience with things like data table. If you don't, then don't give up, because to me, I found one of the most useful things in learning to code is absolutely watching people do things more advanced than what I could do, but not just a bit more advanced, quite a lot more advanced. So it's sort of head-spinningly more advanced, and then trying to figure out bits of it, because then I always had something sort of bigger to aim at. So you'll certainly recognize all the basics, things like indexing and variable assignment and things like that, and then you'll see other things that maybe in some cases the functionality will be so obvious to you that it's that you can pick them up just by watching the video. Let's see. So what we need first is that at this given site, at this given locus, there's going to be a certain number of segregating variants. So we'll need to tabulate, and in fact we'll describe the population at each stage as just a table that describes all of the different variants in the population at that stage. So what do we need to know in order to characterize that whole population? We need some sort of identification for each variant, so we'll just choose an integer for that. So this is the constructor function for a data table. Here we go. Called segregating variants, and yep, so we have one column for an identification for each variant, and then another column that tells you the frequency in the population. That's what we're interested in following, because that's evolution. And then a selection coefficient. I'm going to give each variant sort of randomly assign them a selection coefficient that describes whether they're beneficial or not on average, and we'll see how that affects the way that they proliferate through subsequent generations. So that will describe our whole population at any given generation. Of course, we'll probably add a column later to tell us what generation it's in when we're recording what happens over time. So to do things to this population, I'm going to have a subroutine for each thing I do for them, and one is going to be just to introduce new variants to the population. So what are the parameters that you might need to describe the introduction of new variation in the population? Remember, this is things like mutation, deletion, whatever. Well, certainly the rate. How many are going to, on average, happen per generation? I mean, are we expecting 10 per generation, or are we expecting to wait for 1 million generations before we see one new version of the allele pop up? The population size, well, that affects the introduction frequency, because if the population size is 2, and you have a new variant, then instantly your new variant is 50% of the population. Of course, that doesn't very often happen. In a large population, you're very small fry when you have a new variant. You're just one in 10 to the 6 or 10 to the 8 or however big the population is. And the selection coefficient is the variant going to be beneficial or not? So I think this function, as I said, is to come up with new variants, hence the name of the function, new variants. And it's going to generate them randomly. So I said, look, what's the average selection coefficient that a new thing will have? And what's the spread? What's the standard deviation, which I set to a very low value. So how many new variants should we add? I think it's fair to use a Poisson distribution. Now the Poisson, for the sake of memory, or maybe for the first time for some of you, that's what describes you're sitting at the side of a road for 5 minutes and you count how many cars go past in that 5 minutes. And that number of cars for the one period, and the next 5 minute period, and the next 5 minute period, and the next 5 minute period will be different, but assuming the sort of, the amount of traffic on the road stays the same, you'll end up with a distribution of how many you see in that 5 minute window. That's a Poisson distribution. So I thought that's a defensible distribution to draw from something like, how many mutations are we going to see within this one time period or generation or whatever you'd like. Bit arbitrary. So we're going to draw it from that. And of course, so in the first step, we ask how many new variants are we looking at here, and we draw it from an R plus random from a Poisson distribution. We just need to draw once, and the parameter that affects what we're likely to see is the rate. That's in fact the average. Actually, it will turn out to be the average of that distribution, or the average of draws from that distribution. Now we have an if statement that just says, look, if we are actually generating any mutations, and in most generations usually we probably won't. But if we are, then we're going to just generate them in the same format we did earlier. So I showed you that tabulation where we had each variant expressed as an identification and a frequency and a selection coefficient. So we're going to generate that, and if we have no mutations, I'll generate the same data structure, but it will be empty. It'll just have nothing in it. But it's of course more interesting when we do generate new mutations. The first thing we'll do is give it an identification code. And I want every new one to have a new identification code. So I've had to create a new data structure. Actually, it's just a one-item vector called new variance auxiliary. And it just says, well, look, what's the last identification code you gave to anything? And when it assigns a new one, it just takes that, it adds one new variance or plus one, it alters that little data structure storing the last ID we did, and it assigns it with an equal sign to the column ID identification. And the next thing it does is it tells it what frequency, and the frequency of a new mutation. Well, it happens in one individual, and so it's one out of the population size. If the population size is 100, you get a new mutation. That mutation is at frequency 1%. So it will work that out here. And a selection coefficient, which I just generate randomly because we're interested in the exercise. So we'll draw from a Gaussian distribution, random normal, as it says. Generate one value, and then it's going to be centered around this argument that we gave at first. I defaulted that to 1. That just means neutral. And it's going to have a spread or a standard deviation that you can also set. I made that quite small. I don't want them to mess around with really big selection coefficients. I think that will be an ugly example. Okay, so that's the way we add new or we create new variants to add to a population. Now, this one I don't think I'll go through in detail, but all it is taking those new variants and putting them in the population. And the reason I need a different function for that is because when you put new variants in a population, the frequency of all the old ones changes a bit, because if there was an old variant that was previously 50% of the population, and then suddenly a whole lot of new variants came into the population, suddenly they'll be a little bit less than 50%. So we have to make that adjustment. And yeah, if you're new to it, challenge yourself to understand this function. It's not too difficult. But it's a function I can call. I get my list. I've just called it dt for data table, and I get my new variance, and it will plug one onto the end of the other and adjust everything accordingly. And what did I just do? That's not what I want. Okay. So frequencies next generation. This is the evolution function. So it says, let's take all the frequencies of all the alleles in one generation, and let's generate the next generation based on what happens there. So we're using the fisher-wright model of the population, and in the fisher-wright model, it just pretends that there are sort of slots in a subsequent generation for individuals, and each slot is going to sort of randomly just pick a value from the previous generation. But that value is, of course, it's more likely that it's going to pick one that's a very high frequency. If just about everyone in the previous generation has allele number 3, then it's probably going to end up picking allele number 3. But I just wanted to adjust this a tiny bit and say, look, if allele number 3 is pretty frequent, but allele number 2 is slightly less frequent, but allele number 2 is terribly advantageous, I wanted to increase the chance that it will pick allele number 2 just because it's selectively advantageous. This is in effect, I mean, I've described it going as though it's looking backwards in time, but of course what this simulating is that going forward into time, allele 2 has actually got a bit of a boost to survival over allele 3. So it's likely to have more copies than it previously did in the previous generation. So I wanted to reflect those things. Now we use a multinomial distribution, but the binomial is the simple version of this one. That's where you've got, let's say you have a coin flip with a biased coin. So the coin, instead of about half and half heads and tails, let's say it just gets 10% heads. And the binomial distribution describes, I tell it, I take a coin like this, and I'm going to flip it 100 times, and how many heads am I going to get? And it will tell me, well, there's a certain percent chance of you getting 1 head, a certain percent chance of 2, certain percent chance of 3, certain chance of 4, certain chance of 5. It will give you the percentage chances of getting a certain number of heads of each kind. Now the multinomial distribution is just like that, except instead of being a coin flip, imagine it's maybe a die. There are 6 options. Or you can have, those crazy dice they use in Warhammer, a D4 or a D20. So there are lots of different options, but again, they're not evenly weighted. They're, with a D4, there might be an option of 25% the first one, but 20% the next one, 30% the next one, 25% the last one, or something. So they're unfair. And you ask at the end, look, what are the chances that I'd get 1 1, 3 2s, 4 etc. a certain thing, and it will tell you the chances. So I'm going to randomize using that kind of framework. So randomize from a multinomial distribution. I just want to randomize once. The number of choices I'm going to make is going to be the size of the population. That I'm assuming is going to stay the same. And now here are the relative probabilities of each of the things. How likely is it that this guy is going to get chosen for the next generation? And we're talking about variance here, remember. So how many of these variants are going to get chosen? Now, that has to be dependent on the frequency. If something is very frequent, it's more likely to get chosen. And the selection coefficient, how advantageous is it to have? So all I've done is just take a frequency and scale it by the selection coefficient. Very simple means of implementing some kind of selection. And then I divide by the population size just to turn it into a proper proportion. Right, so that will take one generation with all its frequencies and produce randomly. It will show how it evolves into the next generation. We're sort of done. We can set up how to run our model now. First, we need to create an initial population, which we do. This is just the same template as I showed above. Essentially, that was just a template used for mnemonic purposes while I was coding, where it had the ID of each variant and the frequency and the selection coefficient. And now we're just going to do the same thing, but we're going to start the population off in some state. So I've said the ID will be 0. That little L there means it's going to be represented as an integer. internally in the system. But don't worry about that if you don't recognize it. The frequency, 1. 100% of the population. They've all got variant 0. Selection coefficient is 1. So variant 0 is neutral. And the generation. Now we need a column to keep the generation. And you'll note that when I assign this, I'm not just starting a new table of variants. I'm also saving it to. All right. So we had another crash, and it's going again. So let's just finish this up as quickly as we can because I want to eat dinner. Right. So. We ended where we're just ready to begin our simulation and we're setting it up. So we have a table here that describes all the variants in the population. Each one has an ID, a frequency, a selection coefficient. And this time we're going to set it up with a little record of the generation because we're going to save one each generation. And in fact, to save the first generation, we've used this little trick with the multiple assignment operators either side of a variable name. So we've got the first initial state saved not only in the record keeping thing, but in the table that just updates constantly to reflect the state of the new population each generation. And we started the first one with the ID being 0. The frequency is 1. Everyone's got this. Everyone is of this variant. The selection coefficient is 1, it's neutral, and the generation may as well be 0, and we'll just increment that upwards. So, new variance, that's the auxiliary variable that just tells us that the current ID is going to be is 0, and we'll go upwards from there. Time max, the number of iterations, the number of, if you like, generations perhaps. Population size, I tweaked these numbers to get nice informative results earlier, but that's a good one. And then these are the parameters affecting the introduction of new variants, mutation, if you like. So the lambda is how many new variants per generation. So I've set it to 0.1. The average number is actually less than 1 per generation. So we expect to go through a number of generations for every new. Until we see a new variant introduced. And then on average, this reflects the selection coefficient of any mutation. So on average, mu, it's 1, and the standard deviation is just 0.5, very low. So they're usually very, very close to neutral. Now, this is the function that runs it. ldply, this is one of the apply family functions. Apply family is just a loop. We should just call them loops, but it's loops for R. So we're looping over from 1 to time max, so 1 to 500, and each time we do it, that variable, whether it's 1, 2, 3, 4, 5, 500, will get stored under the name gen. And these are the different steps. First, we ask, do we want to introduce new variants? So we use our function that we defined above and ask, could you generate some new variants for us? Or if not, just an empty data table. And then we add them into the population. So our population is described by the data table segregating variants, and we add them into that using the function we defined earlier, and giving it the new ones and the old ones. It puts them together, and we overwrite our current state. Then we do the evolution. Again, we overwrite it with the next evolutionary stage. And it will choose the new frequencies of each of the variants in the population based on the function above. Again, here in this one, we need to write the new generation number in at each, because we've entered a new generation, so we need to overwrite the new state with a new generation number just for record keeping purposes, if you like. And as far as record keeping goes, again, we take this thing, save history, and we overwrite it with itself plus the state of the generation of the new thing. So we row bind the old version and the new version. And of course the new version will have a new generation because we did that in this step. And then I just get all the variants that are frequency 0 and I delete them. Why? Because they're frequency 0. They've gone extinct. They cannot come back from extinct. So I delete them. We can run that, and I've run it earlier and got a nice result in one of the previous videos, so I'll just leave. I won't run it. It takes about 20, 10 seconds to run. And we end up with, oh no, I must have overwritten save history, so we have to run it again. Let's see if we get a nice result. So there's save history. You can see, for example, at the beginning, the population during generations 1, 2, 3, 4. Each of those actually seems to be just one variant still at frequency 1. But by the end of it, oh, we've still got frequency 1 by the end, and the IDs are 33. So we've seen at least, oh, sorry, that's weird. So we've seen, there's an ID of 59. So we've seen at least 59 new variants being introduced. Just seems like none of them really took off. Actually, let's go ahead and plot it and see what happened. And we can try generating this again if it didn't produce at all an interesting result this run. So we use ggplot to do that. We feed it our history, our saved history. And we're going to use the aesthetic. Yes, this function aesthetic dictates to ggplot what it should plot as the different parts of the graph. So on the x-axis we'll give the generation, and on the y-axis we'll give the frequency. We're going to create a bar plot here. In fact, we're going to create a stacked bar plot so that each column is divided up by frequency equally by the different alleles segregated in the population. And I thought we could color each of them according to its selection coefficient, so we can see how the selection coefficient affects the way it evolves from generation to generation. So let's generate that. That's too close together, so we'll just move that across. Ah, that's something interesting. We can talk about that, sure. So look what happened here. We started out with one allele, and it's at 100% frequency, so it's just one bar the whole time. And you can see little wiggles around the top here, just very subtly, right? That's what happens with most generations that have ever happened in the history of evolution. Most new variations, even the ones that would have been so beneficial that they would have just knocked everything else flat, have just gone extinct. They've had to, they're just not high, just randomly they change, they wiggle around over time in frequency, they just go extinct, no matter, even if they're really beneficial. Now, here's a cool event. So you see the introduction of a new variant, and this area here that represents that new variant, you can see that's slightly lighter than the one below. So it's slightly more beneficial, but not too much. So it's still going to wiggle a lot, and in fact, it does wiggle. It wiggles all the way back to where it almost goes extinct here. This would be, yeah, a nightmare. Real nail biter, white knuckle stuff for that allele, but it does actually hold on, and it stays at low frequency. But what happens in the meantime? You can see a new allele has been introduced. This is a lighter color, much lighter, because it's a significantly better selection coefficient than this previous one, and that quite quickly dominates the population. This really happens in real life, folks. This would be a selective sweep on that area, and you can see a few sort of less advantageous alleles get introduced, and they have a crack, but they never quite catch on. They're a bit, they're like Rebecca Black's career in that sense. Let's just do one more for fun and just see if we get an interesting history that time. Okay. What? Oh, I didn't overwrite my old. I didn't overwrite my old saved history, so I've ended up with a strange frequency plot. Yeah, I have to reset everything. Okay, new table. Let's see what we get here. Oh, another great history. Look, here's something interesting. So we've got almost a similar situation here, actually. Things with similar selective advantage. One sort of invades a little here and then comes, and now we've got the increase in frequency of something that's slightly more fit. You can see this allele here is slight selective advantage, but it actually gets overtaken. Because all the alleles, just by chance in this population I've simulated, come in with pretty similar selection coefficients, actually end up with 1, 2, 3, 4, 5, 6, 7 alleles segregating in this 250 individual population at one time. Anyway, you can tell that I get excited about evolution because of thinking about things like this. Programming a tool like this is and playing with it indeed is absolutely wonderful for your understanding of it. So I hope that this hasn't been pitched either too high or too low or too fast for everybody. But if you are interested in doing these things and you would like a tutorial that either goes much more slowly and does it in 10 parts, or looks at the actual, focuses more on the evolutionary theory, or focuses more on the coding and just teaches you how to use, say, data table to create a thing like this, I would be very happy to produce one or to share my code or to answer any questions. But now it's almost 9 o'clock. My girlfriend's coming back from Croatia in a few hours, and I think it's time for me to sign out of the New Scientist Twitter and say goodnight. So if you've made it this far, congratulations, and it's been a real pleasure. Take care.